we've got, if you've looked at homework 6 or gotten started already, the first couple questions are work questions, but at the end, there's just a bunch of sequence questions. And just to check, since this is going to it's going to come up a little bit today, we will also need to talk about telescoping series, at least do one example of these, of indeterminate forms. You guys remember all these from Calc 1? So something like, I'll leave number 4 to you guys. I will kind of say it's a little tricky, or it's just something that we don't recognize very often. We like to use L'Hopital's rule whenever we can. It's kind of a quick and easy rule to deal with indeterminate forms. But remember, L'Hopital's rule only deals with infinity over infinity or 0 over 0. So we want to find limits of sequences like this. And well, what's going to happen? It's going to go to the infinitieth root of 7 to the 1 plus 2 to the infinity, which is the infinitieth root of infinity. What does that even mean? Could that be a finite number? It could be infinite. So these are the types of things where you have to kind of remember all of the tricks. So this one, I think you can probably manipulate it algebraically by just remembering how to factor your exponential functions, and perhaps try to see if you can factor out a 7 from that, and then in some sense try to cancel or manipulate the square root as an nth root and do algebra that way to simplify this guy. So that shouldn't be too bad. I did want to at least get you started a little bit more. So on number 7, so what's going on in number 7? You've got 1 plus 2 over n to the 3n. And so now what's happening with this guy, when we compute the limit, we will get essentially 1 plus 1 over infinity, which is a 0, but then raised to the infinity. So it's 1 to the infinity. And remember, a 1 to the infinity is indeterminate. Because really, it's slightly bigger than 1, right? Every term here is just going to be smaller, just slightly bigger than 1. And then if any number slightly bigger than 1 is raised to the infinitieth power, it should go to infinity. But at the same time, the number that it's slightly bigger than, it's so small that it's really getting closer and closer to just 1 to the infinity. So we want to actually be able to figure out how to deal with these guys. And so just a refresher of Calc 1, how do we deal with these guys? You really want to think of this guy as a function. And now we want to just compute x going to infinity. We will get the same thing, this 1 to the infinity. So how do we deal with it? Whenever we have an infinity in an exponent, we apply natural logs. Because natural logs allow us to bring down that exponent. And now if I take the limit of both sides, this guy's going to go to infinity times natural log of 1, which is 0. So still an indeterminate form. 0 times anything should be 0, but infinity times anything should be infinity. Whenever we have these contradiction of principles here based on the properties of a number and how it behaves, we get these indeterminate forms. So we're a little bit closer, and now what we want to turn this into is something like a 0 times a 0, or infinity over infinity. And so the best thing to do is probably keep your natural log in the numerator. And for the sake of not messing too much with the constants, let's go ahead and keep the 3 there, but then divide by 1 over x. So this expression on the right, these two are the same, right? Just algebraically manipulating it, making it look different. Because if I make it into a fraction, now what's my limit as n goes to infinity, or excuse me, as x goes to infinity? We're getting 0 divided by 1 over infinity, which is 0. So just to get you guys started on that, once we're here, now the next step, we can apply L'Hopital's rule. So now you can take a derivative of this numerator, take a derivative of the denominator, do some algebraic simplification, compute the limit again. And just remember, we applied, the first step was to apply the natural log, which means the last step we have to undo the natural log, which means we need to exponentiate. So once you do L'Hopital's rule, whatever you get, I will say simplify, do the algebra, then compute the limit. And once you should get some finite number. Remember to just exponentiate at the end. This is really our limit of the natural log of the function. And so to undo that natural log, the limit of the function should be e to the c. Okay. So let's review a little bit of what we did yesterday, just to do a few examples, kind of warm ourselves up here a little bit more. Just test for divergence. If we see a function, or excuse me, a series, and the question is just asked, determine whether it converges or diverges. We've got n squared over 5n squared plus 3. From 1 to infinity. The first thing we should check is the individual terms. So the sequence of terms that we are adding together is just this n squared over 5, n squared plus 3. And the limit as n goes to infinity of an when I compute that limit, it's a polynomial. Numerator and denominator have the same degree, and so our limit is 1/5. What does that mean? If the individual terms don't go to 0, then the series diverges. By the divergence test. So the terms don't even go to 0, nothing more to do, it just diverges. So that was the first thing we saw yesterday. And then we were talking about geometric series. So let's do one that's a little bit trickier. We saw some things that looked very similar to what I'm about to write. So this is 2n minus 2 over 5 to the n plus 1. And one of our first goals is to trying to get our ratio, try to get it something like r to the n times a constant. And so with these different exponents going on, where I've got a 2n minus 2 and n plus 1, we need to remember how to do the algebra of exponential functions to get it look like something like some constant to the n. And I can determine from that constant our multiplicative r value of what we call it, of whether or not it's going to converge or diverge. The other thing I want to practice a little bit is, well, what happens if we have a sum, let's say starting at 3? This is just some extra algebraic skills that you can see. The starting value is not going to affect whether it converges or diverges. Doesn't matter, because if we start, if we start at 3, really all that's saying is, well, I'm leaving off the first term and the second term when n equals 1 and n equals 2. It's kind of like, well, let's forget about those terms and just start later in the sequence. I'm still adding up an infinite number of terms, and the test of whether or not adding those infinite terms will converge or diverge still only depends on the rate of decay, on that r value that we get. But if we want to actually find the value that it converges to, well, now I'm going to have to actually deal with what happens if I leave off those first two terms. And there's a couple of ways we can deal with it. So let's do the algebra of the exponential functions first and try to get this looking nicely in terms of something to the n. So let's deal with the numerator. So this minus 1 to the n is good. It's a constant to the n. So we're just going to keep it hanging out as we manipulate everything else. The 5 to the n plus 1, so let's start with the denominator because that one's a little bit easier. If I have an n plus 1, the n is nice. It's just the plus 1 we have to deal with. And the plus 1, all you have to do is factor out 1 power of 5. And now I have that 5 to the n there. And we are completely fine with multiplying by constants because I can pull constants outside of the sum. We want to do something similar in the numerator, but the problem is we've got a 2n here. So anytime you have like a 2n or a 3n, it's never going to be too complicated like an n squared. Usually the examples we like to stick with are some sort of linear function upstairs in an exponent. So you usually want to try to just factor out whatever that constant is, right? If I want it something to the n and not that 2n, let's factor out that 2. And just a fair warning, I mean, I wrote it as 2n minus 2, so that 2 is going to factor out of both of those terms in the exponent. I could have had it as like 2n minus 1, and then when I factored it out, it would be 2 times the quantity n minus a half, right? Sometimes the numbers aren't so nice. Most of the time, hopefully they will be, and we're not going to throw really complicated, 1/2 exponents, which we can deal with. They are square roots. But for the sake of just practicing the skills, usually the examples are a little more convenient numerically. So we're going to have this as 2, and then in the exponent, we're going to factor out that 2. We're starting at n equals 3 to infinity, minus 1 to the n. I've still got the 5 times 5 to the n. And then now, once you factor out that constant, you essentially want to manipulate that. So this is just going to be 2 squared. And now when a multiplication in the exponent, we can think of as some sort of exponential operation then raised to another exponent. So I can put the n minus 1 upstairs. And now I can do this 2 squared. So let's do the next couple of steps. We'll have a minus 1. So 2 squared is just going to give me a 4. And I'll have 4 to the n minus 1. This one's a little bit different than what we had to do with the denominator. We're back to this case where it's just a shift, a plus or minus 1 or a plus or minus a constant. And In this case, we can't quite factor out a 4, because if I pull out another 4, it'll be n minus 2. Instead, what do we have to do to deal with this minus 1? Forgot that in there. We actually have to divide by an extra power. So n plus 1, or if it's like an n plus 2, right, I can always factor out sort of in the same location, whether it's the denominator or numerator. If I have an n minus 1, what we're going to do, and let's just keep our terms grouped here for a second. So 5 times 5 to the n. This 4 to the n minus 1, I'm going to write as 4 to the n divided by 4. Right? Because here, if I wanted to just work with this term, I would subtract the exponents, because that's a 4 to the 1. So all in all, I have my constants. I've really pulled out this 5 and 4 now in the denominator. And I'll just keep it as 4 times 5. And now what do we have? We have a minus 1 to the n, 4 to the n, over 5 to the n. In other words, so I'm writing all of this out. Of course, if you're following the steps, not all these steps are incredibly necessary to write out, but this is kind of the first time we've seen some of this. So I do want to, just to make sure we have all the steps written out, and at least one video kind of demonstrating all this. We can write this as minus 4 over 5 all to the n. All right, so if you want to go from here to here, we can kind of skip that one. And, some of these other ones of our algebraic manipulation, you can always do the numerator and denominator at the same time. Save yourself a little bit of writing if you're following and you're comfortable with these steps. Okay, but we've arrived at what we wanted, something to the n. And our r value in this case is minus 4/5. And that's good, because in absolute value, it's less than 1. Really, what this absolute value of our r being less than 1, you can think of it just as numbers between -1 and 1. So as long as we have some fraction, whether it's positive or negative, a fraction that is between -1 and 1, we know that this will converge. So that's the first step. We know it converges. The next step, though, what does it converge to? And we can't use our normal formula, right? We have a formula where it's r over 1 minus r. We want to use that, but we can't use it quite yet, because that formula is specifically for n equals 1. So let me get a new page so we can have some space to work through this next set of algebra. We've got 1 over 20 times the sum of -4/5 to the n, but our n is starting at 3 to infinity. And our note was we can't use r over 1 minus r yet, since this holds. When n starts at 1. In other words, we will have a sum of 1 to infinity. And now I've got a 3. So how do we deal with that? So this will come in handy for Taylor series as well. And I want to start off with the hard way, just because I want to see you guys, I want you guys to see it, because it's going to come in handy with harder polynomials. Essentially what we're going to get to with Taylor series is polynomials that are infinitely long, infinite degree polynomials. And it often helps in understanding how to manipulate our variable. This is essentially like doing a U-sub. So I'll write it down. Let's call it a change of index. This is like a U sub. And in fact, it's kind of like doing an easy U sub. We've seen these cases when we need to do U subs where it's just a linear shift, where our x is, or we let u be x plus 1. And then our dx is still du. We're kind of just, in some sense, we're just shifting the starting value left and right, where here our n is like our x variable, right? And now it's saying, well, let's just start over at 3. And so what we want to do is kind of just take our frame and kind of shift it so that we're starting at the correct value. So let's explain what I mean. Well, we start at 3. Let's pick another variable. K or I are commonly used. I don't know if that's shown up on the WebAssign. Usually our index variables, I, J, K, and N are very common for our integers. What do we want? Well, it starts at 3. We want this. When n equals 3, we want k to equal 1. Likewise, the next value is going to be n equals 4. That should be the second value we want. So we just kind of need to come up with a basic linear relationship for that. So if n is equal to 3, let's say let k equal to n minus 2. Does everyone see that? You shouldn't need to write down a whole lot of numbers here, but we can kind of see that whatever our n value is, I really just want k to be 2 less than that. So we start at a different value. So if I let my k be n minus 2, that's what we want. Well, I've got n's in here. We can also solve this for n. So that implies that, well, n is just k plus 2. So just like we did with our integrals, we're now kind of going to change the variable on our sums. What does our sum become? So let me label that as star. And so star is going to now equal, constant's still going to hang out. We're still going to have a minus 4/5 to the n, but n was now k plus 2. And what did we see? This was changing the variable. Now we need to change the bounds, like the bounds of integration we change. Well, we set it up so that when n is equal to 3, k is 1. And of course, when n goes to infinity, what's k going up to? Still infinity. So this is our sum now. And now it's nice because we're starting at 1, and we just got to do a little bit more manipulation. So let's go ahead and do that. We can pull out essentially 2 powers of this guy. So I just factored out minus 4/5 squared will give me those extra 2 when I factor them out, and now I can use a formula for this. So we'll have 1 over 20 minus 4/5 squared. And now I'm starting at 1. My index is k. I can use the formula minus 4/5 divided by 1 minus a negative 4/5. So just to start the algebra, I don't want to finish it. It'll be minus 4/5. Of course, that'll be plus, so it'll be 9/5 when I change the denominator, and of course, dividing by 9/5 is multiplying by 5/9. So a lot of things will cancel. I'll leave it to you guys to check the simplification on that. Take a look at this video if you kind of were a little confused at any of those steps. Good thing to kind of practice just the basic algebraic skills that I just did there. Otherwise, an easy method for doing that, or at least another way we can do this, is we started with 1 over 20, n equals 3 to infinity of minus 4/5 to the n. We started at 3. The other way we can think about this is to say that it was, well, 1 over 20 times the sum. Well, if I start at 1, I'm adding 2 terms. So this isn't the same, because this guy has more. What we can then do is just subtract off the first 2 terms. So this was similar to when we had those indefinite integrals from like 3 to infinity. And well, when we first kind of started and I wanted to do a comparison test or something, if I wanted to compare it with an integral starting at 1, we could always break it apart. Integral from 3 to infinity is the same as an integral from 1 to infinity minus the integral from 1 to 2, or 1 to 3 is where the integral would be. But because it's a discrete system in this case, we really only need to subtract off the first 2 integer values. So our other way of doing it is to set it up like this. We can now use the formula for this piece. And of course, we still get our minus 4/5 over 1 plus 4/5. And now you can just subtract off, you can just compute these by hand. So what is it going to be? It's going to be 1 over 20. When n is equal to 1, we'll have minus 4/5. When n is equal to 2, we'll have 16 over 25. Since there's only 2 terms there, we can just add those and write out explicitly what that sum means. Some algebra to do in both situations. I actually think the algebra in the previous method, or at least the arithmetic, once you get down to the numbers in the previous method, is a little bit easier. Of course, getting to that point required a little bit of steps, especially if you're not comfortable with changing the index variable yet. This method, little more kind of straightforward to get to where we can just plug in some numbers. Of course, now a little difficult adding these numbers and then finding that expression and then subtracting more fractions again. But either way, check those on your own and see if you get the same number both ways. Any questions on that? Okay, let's do one more example of telescoping series, which we haven't seen yet. This is equivalent to partial fractions. It is the partial fractions method, in some sense, for sums, for series. So we've got the sum of 1 over n times n plus 1 is the classic example for this, from n equals 1 to infinity. I want to know, does this converge or diverge? Well, we'll have some better methods as to even describing whether it converges or diverges here in a second. But the classical way of looking at this is, well, if I wanted to do some sort of partial fractions, we can write 1 over n plus 1 as a over n plus b over n plus 1. And we want to solve for our a and b. And check. So just like the x's, we can check, even though our index ranges don't include 0 and minus 1, it should still hold that if n is 0, you can see that a needs to be 1. If n is equal to minus 1, then we will get negative b equals 1. And so b is minus 1. So really this sum is 1 over n minus 1 over n minus 1, excuse me, plus 1. So how did that help us? Well, let's just write out terms. If I wrote out the terms here, it would be like 1 times 1/2 plus 1/2 times a third plus 1/3 times a fourth. It'd be kind of hard to see what was going on, whether it converges or diverges, just from looking at the terms. In general, looking at the terms isn't a great way of determining whether it converges or diverges, and it really only works for these partial fractions methods. If we take a look at what's going on, though, when n equals 1, we will have 1 minus 1/2. That's our first term. When n equals 2, we will have 1/2 minus a third. When n equals 3, we'll have 1/3 minus a fourth. And so what's going to happen? We see that this 1's going to hang out, but I'll have a minus 1/2 plus a 1/2. Then I'll have a minus 1/3 plus a 1/3. I'll have a minus 1/4, and then the next term is 1/4 minus 1/5. And as I keep going, every successive term is just going to cancel each other out. So all in all we're left with is just 1 for this guy. So be careful. There are other situations with other, like if we have n times n plus 2, it can get a little wonky when you write out some of these terms. And the way they cancel may not be exactly as nice with some of these problems. But I think you'll have some practice with this on your WebAssign and maybe even your homework before having to do this on a midterm or a quiz or anything like that. Okay, so let's try to take a look at, well, what's some other things that we could say that are going on with this sequence? It's 1 over, if I multiplied everything out, it's n squared plus n. And we actually just saw it converge. The other thing we can kind of think about is, since we did do partial fractions, we can kind of get a sense that, well, the integrals converge. So it brings up an important note I wanted to clarify and make sure we had written down. Most people did very well on these comparison tests for the indefinite integrals. There were a few subtleties that I didn't take off points for, but I want to make sure that you guys are just thinking about things clearly. Because when I look at this sum, this should be something like this. Just like integrals, sums can be distributed or split up over a sum or a difference. But what happens when we're getting this? Well, this guy is infinity, and this guy is infinity as well. So a fake conclusion might be, well, we get infinity, and so it should diverge. But not quite, because what do we have? We have to be mindful of this minus sign. So our infinity minus infinity, indeterminate. Infinity plus infinity, sorry, infinity plus infinity is infinity. Infinity plus a constant is infinity. So I want to just kind of compare that with some of the things we did on these comparison tests for integrals. We saw some things like, you know, the integral of 1 over x, let's now say from let's say from 3 to infinity. So kind of similar. We're starting to do a different place than these integrals, and we want to compare it with a p-series. And a lot of people said this is 1 to infinity of 1 over x minus 1 to 3 of 1 over x dx. The reason we can conclude that this diverges is because it is this guy we know goes to infinity, and this term is a constant. So some people said if one of these integrals diverges, then the whole thing diverges, which wasn't wrong for the situation. You do just have to be careful. It's not necessarily that blanket. It's not just if one of the integrals diverges, then the entire thing diverges. It's because one of the intervals diverges and the other one is a constant, or the other one is a positive infinity. If they're both positive infinity, whole thing diverges. It's because of the constant. If it was infinity minus infinity, then it would converge. So let's compare what we just did. Let's compare that with the integral, right? If we were to take a look at this integral of 1 over now x times x plus 1, and let's just start it back at 1 to infinity. What's going on with this guy? Well, this is x squared plus x. By a p-test, it should converge because it's 1 over x squared. But if you did partial fractions and we actually wanted to compute this integral, you would have something like this. So, of course, the constants are the same in the partial fractions that we just did, and I just pulled out the minus sign. And now I can actually compute these integrals. So we get natural log of x 1 to infinity minus natural log of x plus 1 from 1 to infinity. And what happens if we try to plug this in? We'll get infinity minus 0 minus infinity minus natural log of 2. And it would be wrong to conclude that because I have two infinities there, that this whole thing diverges. Because again, what is this ultimately going to be? This is infinity minus infinity, which is indeterminate. That means we need to do more work. We need to compute this limit and use some sort of algebraic manipulation, or possibly L'Hopital's rule after that, to find the actual limit. So because we're getting an indeterminate form, let's take a look at, well, what are the functions we actually have? What algebra can we actually do? Here it would be, really what we want to do is write it as natural log of x. If you want to consider now, you could either consider combining those, 1 over x minus 1 over x plus 1 in the same integral, or after we do the integration, you can kind of think, well, this is just natural log of x minus natural log of x plus 1, all evaluated from 1 to infinity. So if we think about it that way, we get this guy using our natural log rules. And now what happens when I plug in infinity to this guy? We essentially get natural log of the limit as x goes to infinity, just going to be 1 now, minus natural log of 1/2. And so it's the fact that these two infinities, this infinity minus infinity, they are both the same order of magnitude in terms of their infinity. And we do actually get a finite limit. So of course, natural log of 1 is 0. Negative natural log of 1/2, we could actually just write as natural log of 2 for that guy. So this is what's going on with our integrals. And of course, the same thing can happen with sums. Any questions on that? Okay, so this is kind of a good transition into the activity. We've got this interplay of sums and integrals. We really want to think of these guys as the same thing. So, oh, sorry, someone sent me question 4 on WebAssign 8.2. You guys wanted to see that example. Sorry for not getting to it. If it's not due soon, I can talk about that one tomorrow. Sorry, I didn't see the chat. Let me change my video, or let me share my screen. Let's go to this guy. So you guys can all see this. This is our integral test, our harmonic series and integral test activity. And give me 1 second. Let me plug in my my stylus and my drawing pad. So if you guys want, I don't know if it'd be too hard for you guys to do both. I'm sure you guys are limited to one monitor and can't like pull up this activity on a different screen. Or I don't know if you want to be able to pull up the activity on your phones. Or if you have a printer, you could print it off real quick. Or if none of those, just feel free to follow along. I could even export or save a copy of the work for this if you guys are listed. Actually, I mean, I guess the solutions for this should be posted on the website. But this is kind of a good activity that'll talk us through what is actually going on with these integrals. As we kind of just saw in the last example, the convergence of a series it goes hand in hand with the convergence of a corresponding integral. The values are going to be different because one is a discrete sum, the other one's like this continuous sum. So maybe it's not going to be helpful for us computing specific values of series, sums of series. But maybe at least it can help us get a sense of a test of when a series will converge. So some of this we've already seen, so I kind of want to skip through a lot of this. Of course, we've got our an, and we want to know, or excuse me, an is 1 over n. We want to know, does it converge or diverge? And we've kind of seen the explanation for this. It has us do this first step, compute the first 1,000 terms, compute the first, however many finite number of terms. We've kind of seen why this diverges. So we already know diverges. And if you want, check on your own time, type this sum. You can type in things just like sum. I think if you go to Wolfram Alpha and you just type in sum of like, you say something like 1 over n, and then you say like 1 colon 1,000. I think something like that written in Wolfram Alpha, it'll understand what this computation means and compute this for you if you want to actually do the numerical computations. Of course, I'm not big on numerical computations since you can't use calculators on tests or quizzes. So let's try to figure out more of conceptually what's going on here. So let's take a look. This is our harmonic series. I actually not a big fan of this drawing, but I guess either sort of a right or left-hand sum is going to work. What we're going to end up doing is kind of comparing, well, these sums of series to, in some sense, a right-hand or a left-hand Riemann sum. So let's see what it says. Every series can be depicted graphically. Write down the sum of the series that gives the area of the shaded region below. How does this sum relate to the harmonic series? So what we have is this first bar is height 1. And so the sum of this bar is just 1. Notice that the width of every single bar is just fixed. It's just 1. This is essentially what's going on with our series, is that we're really only considering values of the function on the integers. And if the width of the box is a constant 1, then we can model the height of the box by a function. And that function can be the function corresponding to the series. So the width of the first box, 1, height is 1. Width of the second box is 1, height is 1/2. And let me actually zoom in a little bit so we can get a little more precise with our writing. The third box we see height of 1/3. Fourth box, height of 1/4. So what is the total area? 1 plus 1/2 plus 1/3 plus 1/4, and it continues. And of course, this is just our harmonic series. So the advantage of representing a series in this way is that it can be compared to an improper integral. This is what we've been talking about a little bit these past couple of days with these series. On the graph, carefully draw a function f of x equals 1/x. Let's pick a different color. Let's pick red so it's clear. Well, what is 1/x going to have? When x is 1, we will be at 1. When x is 2, we will be at 1/2. When x is 3, we'll be at 1/3. So you can kind of see where these dots are going. Right? When x is 5, we'll be at 1/5. And so the graph of 1/x, it's asymptotic at 0, but at least starting at 1, let me see if I can do this with this stylus here. It's going to be a little tricky drawing this. It's going to come down, and it's going to pass through each of those points. And then, of course, like 1/x does, it's going to taper off. And so what do we notice? That the harmonic series of 1/n, how does it compare with the improper integral of 1/x? So the best way to say would be this series of 1/n is the left Riemann sum for the integral. With delta x equals 1. Right, the area, the integral from 1 to infinity would just be the area under the curve of all that, of course, starting at 1, going out to infinity. And if we made a Riemann sum, well, with a delta x equal 1, so at our every integer would be our points, we see that this harmonic series is just a Riemann sum where the left endpoints are touching our graph. Does this converge or diverge? Calculate it as a review of improper integrals. So of course we would have natural log of x from 1 to infinity. And what do we get? Infinity. So it diverges, right? By the p-test that we've talked about for these improper integrals. Okay. Let's actually make a conclusion there. They might be walking us through it a little bit weirdly. But let's just at least talk about it. Well, which one's bigger in this case? This sum of 1 over n or the integral? Since we're doing a left Riemann sum and our function is decreasing, you can see that, of course, the sum is hanging out. So the sum of this discrete sum of 1 over n is bigger than the area under the curve of 1 over x. So if the sum of 1 over n should be bigger than infinity, of course, we found sort of another reason, just by comparison, that this harmonic series should diverge, which we kind of already knew. This just kind of confirms that for us. Oh, there was the conclusion. Sorry, I didn't see that part of the problem. Exactly. So we can conclude that the sum of 1 over n will diverge. And so likewise, we want to do the same thing with now 1 over n squared. But look how they drew it. They actually drew it a little bit different. They shifted it over. So instead of starting at 1 and going right, they started at sort of 0 and went off to 1. How is that going to change this for us? And, well, why should it change? The intuition you should kind of be building is that, well, because this integral of 1 over x diverges, the sum of 1 over n should diverge. It's a polynomial in the denominator of degree 1, polynomial in the denominator of degree 1, so they should both behave essentially the same way. So because this one diverges, we can be a little creative with how we draw the Riemann sums, whether we choose a right hand or a left hand Riemann sum to represent the series. Because we had an intuition of that this guy diverges, we wanted to make sure that our Riemann sum was slightly bigger. So that way, if the smaller one diverges, then the sum that's slightly bigger also has to diverge. And this next one, though, well, now we're comparing it with 1 over x squared. And so if we were to plot this points the same way we just did, well, 1 over x squared, when x is 1, we're at 1. When x is 2, the value of the function is 1/4. When x is 3, 1/9. So now the value of the function is on the right endpoints of this series. And if we were to draw this, so again, let me try to draw it and hit all the points. Drops down very steep and then tapers off very quickly. And gets really small. That's our curve of 1 over x squared. And now which one's bigger? Because we chose a right-hand Riemann sum. What did I say? Okay, good. Sorry, my brain's getting backwards. I almost thought I said right for the last one. So in this case, I know that the sum of 1 over n squared is less than the integral of 1 to infinity of 1 over x squared. And of course, because everything's above the x-axis, if we want to make a proper comparison, I know that it's going to be bigger than 0. What do we know about this guy? by our p-test, we know that that guy will converge. And what's it going to converge to? We will have minus 1 over x when we do this integral, which will give me 0 minus -1. So just 1. What does that tell us about the sum? Sorry, I'm just now noticing that we have an n equals 2 here. I am not sure. So this is a subtle point, I guess. We do want to be a little careful with this. So notice that we started at 2 versus starting at 1. This is, again, a shift in finite index. Well, if we truly wanted to compare this Riemann sum, where's this first bar? If we're using our right-hand endpoints, well, it's really comparing the area from 0 up to infinity of 1 over x squared. But we don't want to start at 0 because that's a crazy area for 1 over x squared. For just the finite bar, it's fine to deal with. At least with starting from 2 to infinity, our blocks, our sum is only the sum of these blocks. And the sum of those blocks we want to compare to the area only starting at 1. To infinity. Yeah. So the integral from 1 to infinity is going to be compared with this sum now starting at 2, because we're starting with this block here. And so I know that at least this series converges. What does it tell us about the whole series? And this is kind of one of the things we can do with series that isn't going to necessarily work with this integral, because of course if we extend the integral over to 0, this area below the integral becomes infinite. But we really don't really care about what the integral is doing around 0. We really care what the integral is doing out at infinity. And then these first terms around 0, really we just want those terms of the series. So when n is equal to 1 of the series, this one also has to converge, right? Because this guy is just going to be the sum of 1, which is the first term, 1 over 1 squared, plus the sum of 1 over n squared, starting at n equals 2. Everyone with me on that? And I know that this part converges, so it's a finite number plus 1, still a finite number. Anyone like writing or catching up on anything I've done or said so far? Any questions? So this is kind of our big idea, our big concept. Just by choosing sort of geometrically how we model these series, we can really compare it with a function, either as a right-hand or a left-hand sum of a right-hand or a left-hand Riemann sum of an improper integral. And so this gives us our integral test. Let's write it in red. So the integral test. What are our conditions? Suppose f is a continuous positive. Why am I not writing? Oh, I'm on the wrong layer. Sorry. Let's see. Continuous positive decreasing function. So continuous almost always goes hand in hand. We don't really study discontinuous functions a whole lot in calculus, especially once we get to Calc 2. We do need this positivity. So alternating functions, alternating series, we're going to have to deal with in different ways. And we do need it to be decreasing. And we'll see why here with this rest of this activity. On 0 to 1, and it matches the function on integers is equal to the value of the sequence of terms. Then the series is convergent if and only if the improper integral converges. In other words, so if we know the integral, the indefinite integral of f converges, then we know that the series also converges. If the improper integral diverges, then we know that the series diverges. These two things go hand in hand. Our sequences and the corresponding indefinite integral will always converge or diverge simultaneously. So why do we need decreasing? What could go wrong if our geometric argument? Well, let's draw the picture. Let's get a new layer here real quick. Well, what could happen? We could essentially just erroneously conclude of what's going on with the function. I could have a function that matches at certain integer values, but then does crazy things. So in between the points, it could go up, it could go down, and it could do all sorts of stuff in between. Of course, that's not a function because I drew back on myself. And it could even, spike up and then give an enormous amount of area and then come back down. And so we could get an erroneous conclusion. In some sense, I could have a function that, because it's not, does these crazy things in between the integers, well, it would have to go up, then down, and up and down. It could diverge and not give us any real information of what's going on with the series. Conversely, we could have a function that converges, that comes and it goes all the way down, and because there's very little area that it actually covers, it could diverge, or it could converge because there's very little area in between there, and give us a false conclusion that, well, the series should also converge when the series might diverge. So think of this kind of drawing on the previous example on 1 over n. We know 1 over n will diverge, but if I compared it with a function that is 0 almost everywhere except where it peaks up and matches that function, or the continuous function in an integral might converge, but that doesn't necessarily mean that the harmonic series is going to converge. So we need a monotonic function. We need it to be a nice, smooth, always decreasing, no crazy wavy stuff going on in order to get a good comparison. And of course, that's pretty much anything anyone would ever come up with, right? You're never going to pick a crazy function and have to model it with, crazy bumps up and down to model something like 1 over n squared. The natural comparison, 1 over x squared. And that'll meet the criteria almost always. So, oops. So I'll just say because of bumps and false conclusions. Okay, so we want to determine whether 1 over n squared plus 1 converges. What's the natural function to compare it to? X squared plus 1. Replace your n's with x's. F of x is decreasing because, how do I show it's decreasing? Find the derivative. So what is our derivative? 1 over x squared plus 1 squared times 2x. And of course, it would be negative. So that's just x squared plus 1 to the minus 1. So we get x squared plus 1 to the minus 2 times the chain rule times negative 2x, or times 2x, and the negative, of course, came from the exponent. How do we know this is decreasing? Remember that the bounds, if n is equal to 1 to infinity, we can choose the bounds for our function. It's almost always going to be 1 to infinity is always a decent choice. Sometimes 2 to infinity, as we saw. And actually, I don't think for the series or for the integral we'll ever have to use 2. 1 to infinity is where our x ranges are. And so, of course, if x is always positive, the numerator is always going to be positive, or this 2x will always be positive, times the negative will make it negative, and the denominator is a squared function, so it'll always be positive. So this will always be greater than 0 on 1 to infinity, or excuse me, less than 0. Always going to be negative on 1 to infinity, so decreasing. Check that f of x is always positive. So why is this function, 1 over x squared plus 1, always positive? There's no minus signs hanging out. And any x value I plug in, we're going to square it. So it'll be a positive number plus 1, always a positive number in the denominator. The denominator, and of course the numerator is just a constant 1. Both of those are always positive. So always greater than 0. Everyone still with me? So we're breaking this down, a lot of baby steps here, but good to follow through. And our function now, 1 over x squared plus 1, hopefully everyone recognizes that. We want to, of course, compare the sum with the infinite integral, and they will both converge or diverge hand in hand. And this is an integral we can do. What is our antiderivative with that guy? So we've only got a few minutes, of course, if you forget how to do this, or just forget what the actual antiderivative of 1 over x squared plus 1 is. It's arctan. Oh, sorry, I'm writing that in the wrong spot. So this guy is equal to arctan. One to infinity. What is our limit as arctan goes to infinity? So remember that one was pi over 2. And what is arctangent of 1? Got to remember your trig. Arctangent of 1. What angle has a tangent ratio of 1? It's pi over 4, right? Pi over 4 gives me isosceles right triangle, and the tangent is 1 over 1. So, of course, all in all, the values, pi over 4, which is finite value. So this guy converges. and therefore the sequence also converges. So last one real quick, we've got 1 over n, natural log of n. Let's do this one a little quickly. We're starting at n equals 2, namely because we can't start at 1. Natural log of 1 is 0, and we can't divide by 1. So because we're starting the sequences at 2, we want to compare this with this guy. You want to make arguments. Why is this decreasing? I know 1 over x is decreasing. I know 1 over log x also decreasing. So 1 over x times 1 over log x is still going to be decreasing. The other way you can think about it is I know natural log just by itself is increasing. X by itself is increasing. So I know that x times natural log x is an increasing function. 1 over that will then be the reciprocal. It'll decrease. Also always positive. I'm plugging in positive numbers to x. Natural log is going to be positive when x is bigger than 1. So our x's are bigger than 1. And of course, how do we integrate this? Do a u sub. U is equal to natural log of x. Check that for yourselves. You should be able to find that the integral is natural log of x. So quick check, take a derivative of this guy. It'll give me chain rule 1 over natural log of x times the derivative of this guy times 1 over x. So 1 over x times 1 over natural log of x. And now what happens when I take the limit as x goes to infinity? Well, natural log will go to infinity. Natural log of infinity still goes to infinity. So it'll be infinity, and I wrote the wrong bound there. Infinity minus natural log of 2. So again, we have infinity minus a constant. So that'll give me an infinity. So I know the integral diverges, and we could say by the integral test, the sum will also diverge, excuse me. Any questions on that? So sorry for being a couple minutes over. We'll pick up tomorrow. This test is really useful because now we want to know, well, we want a p-test. So we'll pick right up and we'll say, well, now what values of p will this guy converge for? And it'll be just the same as our integrals because we can use our integral tests to solve this question.